Hi everybody, I'm Sam Hoff, and this is my 8th grade Nobel Prize project. It's about wireless power transmission and wireless charging. Now, the first thing that we need to talk about is current and voltage. Now, current is the actual flow of the individual electrons themselves. If the electrons aren't moving, then the current is zero. And voltage is the potential energy that the electrons have. It's the actual energy that allows current to flow. Now, the first person to really exploit the powers of transferring energy without any wires was Nikola Tesla. He was able to transfer energy using strong electromagnetic and strong electrostatic fields in a device that we now call the Tesla coil. Now, Nikola Tesla created 3 separate prototypes, one in 1891, 1893, and a third one in 1894. And he was able to transfer a small amount of power and information wirelessly. And that was the invention of the radio. Now, one of the most impressive things Nikola Tesla ever built was the magnifying transmitter. And this was a massive Tesla coil that he built. It's actually similar to the one that I built. And it was a prototype that he was using that he was going to use to power entire cities. Now, recently, there's a company called One Tesla that is trying to make Tesla coils more efficient. And one thing that they're doing is they're actually giving kits to people to build their own Tesla coils, which is pretty cool. Now, there are a lot of different types of Tesla coils. The one that I built is called a spark gap Tesla coil. Now, the reason why I built it is it's pretty easy to build and it's not too expensive, but it's not super efficient and it can be pretty large. There's also the vacuum tube Tesla coil, which is a type of Tesla coil called a solid state Tesla coil, which means it doesn't use any spark gap. Now, it's a bit more efficient, but it's harder to use. It's a bit more expensive, but it can be more compact. There's also the transistor solid-state Tesla coil, which is a lot more popular. The efficiency can be high or low, um, depending on the model you try to build, but it's not super hard to use. It doesn't have to be really expensive, and it can be very small and compact. The dual resonant solid-state Tesla coil is the most efficient. It has ultra-high efficiency, and it's pretty hard to build. It can be pretty expensive due to IGBT transistors and complex interrupter circuits, but it doesn't have to be very big. Now, one of the problems with Tesla coils is if you run it in an enclosed area, it can produce ozone and some ultraviolet light, and it could even interfere with some radio frequencies. But if you take it outside away from any sensitive equipment, it'll be just fine. Now, the pros of having a Tesla coil for your wireless transmission system is it can be very efficient, it can be pretty cheap and inexpensive, and it can have pretty long range. But it's limited by the inverse square law, and if you're using a very large spark gap Tesla coil, a large oil transformer could produce explosions or harmful arcs. Now, here's just a quote talking about how it could be dangerous if you run it in an enclosed area and produce some harmful gases. Here's an experiment that I think is pretty cool. It's where they're using wireless transmission pads to actually power someone's medical device without them having to be chained to a bed, which I think is pretty cool. Here's another experiment that's pretty cool. It's where they wirelessly charge the batteries of drones with the Tesla coil. Alright, now that was my slideshow. I hope you enjoyed it. Now here's a video of me running my Tesla coil. Okay, so this is my Tesla coil that I built by myself. So the first component for a Tesla coil is the high voltage transformer, and this is the one I'm using right here. It's 15,000 volts at 30 milliamps. This specific transformer is often used to ionize the gas inside of neon lights. And we actually got this from this retired electrical engineer, and he sold us 6 high voltage transformers, and the one I'm using right here
operates at 15,000 volts at 30 milliamps, and that's a lot of power. I also have this one right here, which is a 7.5 thousand volts at 30 milliamps. And so basically this takes the 120 volts out of a wall outlet and it steps it up to 15,000 volts on these two outputs right here. So we get that voltage coming from the transformer, and that power goes into a component called a capacitor. Now, I made this capacitor out of 2 pieces of aluminum and an old trash can. So the way a capacitor works is you get 2 metal plates and you have a spacer in between them called a dielectric. And the way I made mine is I have the 2 pieces of aluminum on the outsides and I have the trash can as the dielectric or spacer in between them. Now the electrons will build up on the edges of these plates right here, and a lot of power can build up on those 2 plates. The next part is the spark gap. Now I made my spark gap out of these 2 bolts right here, but there are a lot of different ways to make it. Basically it takes the voltage that builds up on the plates of this capacitor right here, and when that voltage reaches a certain level, very quickly all that current dumps across this spark gap right here. And when it fires, it's extremely loud. And I actually have to wear ear protection while running this. It's crazy. So that happens every 60 seconds due to the AC frequency. Now here's where things get interesting. All of that energy that gets dumped across the spark gap goes into this component right here. And this is one of the 3 components of the Tesla coil, or the main body of the Tesla coil itself. This is called the primary coil, and it's a couple turns of very thick wire. One of the other components is the secondary coil. Now this may look like just a green pipe, but it's actually 1,200 turns of very thin wire. The last part of the main body of the Tesla coil is the top load right here, and this basically lowers the resonant frequency of the secondary circuit. Now, the capacitor and this coil actually serve another purpose, and this is to resonate with each other. Sort of like when you hit a tuning fork, it resonates at a frequency. Now, the frequency that this resonates is about 100,000 kilohertz, or even a little bit above that. Now, that will increase the voltage on the secondary coil, and the coil itself is going to produce high-frequency electromagnetic fields, and the top load right here, this is where the electrostatic fields come out. And the way we test this is with this light bulb right here on a stick. And when you hold this up near the coil, it actually lights up without anything touching it, which I think is pretty cool. This right here is another prototype Tesla coil that I was building. It has some turns of wire right here, and this is a coil that I actually wound myself. It has around 300 turns of wire on it. Now check this out. Here's a video of the Tesla coil at its current state running. Now it's not fully tuned yet, so we won't be getting huge bolts of lightning coming out of the top, but it did light up a light bulb from a good distance away.
2, 1.